All right. All right. So let me give some background on this library and what a virtual DOM library actually means. So I basically am very interested in web user interfaces and things and user interfaces in general. And the thing about user interfaces is that they are very stateful in nature. And usually, before virtual DOM libraries came about, a lot of the UI code that was written was very stateful and very non-pure in nature. So if you look at old libraries, like, for example, Java Swing, that's the library that I had most experience with before I started doing functional programming, user interface development. So the way they work is that they will basically have, so you will have a function which will set up the initial user interface. So it will say, create a window frame. That'll be one line. And then the next line will say, okay, put a button inside that window frame. And then the next line will say, okay, set the text of that button to this. And then attach an event handler to that button that will basically perform these steps. And then inside that event handler, you would again have a very imperative, mutate-y sequence of things that happen. So it would be something like when that button is clicked, change the text of the button to something else, right? So it would be a simple way of creating a user interface with a button that does something when you click on it, right? But it's all very imperative. So when people started thinking about how to build user interfaces in functional programming languages, especially languages which are pure, so the problem that came about was that how do you encode all this statefulness and all these imperative sequence of events that happen, right? And the natural thing that came about was FRP. So FRP is basically a way to introduce reactivity into your application by specifying sort of a graph of how the dependencies are between the various components of your UI and how they update based on response from events from other elements on the page, right? So there are lots of FRP libraries. Those were the first UI libraries that came about with FP. And there were libraries like Reactive Banana, and I think Yampa was the first Haskell library that did that. And then came a language called Elm. And Elm basically came up with this concept of a virtual DOM structure, which basically is a lot simpler way of creating user interfaces. So in virtual DOM, what happens is that you basically create a tree of all the user interface elements, and then which is like a conceptual tree. So you would have a data structure that represents what your UI looks like. And on every state change, you reconstruct that entire tree in memory. And then the virtual DOM engine, it takes the old tree and the new tree, compares them, sees what the differences are, and then applies those differences in one go, right? So we went from a state of single stepping imperative sort of a UI update. We went to this entire functional set of functions. So it became like it got divided into multiple steps. The first step is creation of a UI tree, right? That's what the initial UI will look like, and that is entirely pure. You just specify that, okay, initially I'm going to have a data structure that will represent a window frame, and inside it I have some children. In that children I have a button, and that button has a text, right? So it's all pure and non-imperative. And then use what happens when you click on that button, right? You again construct the entire tree again. So it does not depend on the previous state. There is no mutation happening here. You again construct the entire tree and you say that, okay, this time I want to create the entire tree, but I want to have a different text on that button. And then the VDom engine, it does this diffing and sees, okay, the tree's changed in this particular way. And it does it efficiently. So it has some tricks on. So one of the responsibilities of a VDom engine is to ensure that the updates are efficient. So it does that diffing. It does patching of the virtual DOM, of the DOM. And when I say DOM, I mean document object model, which is basically a word for UIs in the web. So it updates the UI according to that diffing. and it does everything efficiently. So that became a very functional approach to building UIs. The responsibility of a VDom engine is basically to be able to take an entire tree that represents your UI, diff it with the previous tree, create a diff structure, and then patch that diff structure over to the actual UI. And that's what a VDOM engine does. That's really all it does. And then libraries like React and other, so React also adopted the whole VDOM idea wholesale from Elm, and then ran with it, and VDOM became really popular for web development. So in React, in Rust, it's an imperative language, but then people realize that, okay, VDOM and functional updates and functional UIs, they make sense even in imperative languages, right? So Rust also has VDOM libraries, and lots of imperative languages also have VDOM libraries, because it's just a good way to structure your app. So what I wanted to do was that I wanted to port a UI library that I wrote for Haskell and PureScript to Rust. And that library is called Concur. And the first step that I wanted to do is to create a VDOM engine in Rust. There are already VDOM engines in Rust, but I wanted to build something of my own just to understand Rust better and just to learn Rust. So this project started a couple of months ago, and this is I'm not reading any Rust blog articles or any books. I'm just trying to learn Rust by doing Rust, right? So this is that code. So it may be very rough in places, but I will sort of take you through the code very quickly. And I'm always open for feedback. So and contributions. Like if someone wants to contribute to this, please let me know, and I'll be happy to take patches and stuff like that. Okay, so let's look at this code here, right? So as I said, VDOM library basically has a couple of different responsibilities. First is representing the UI as a data structure, and a UI is naturally a tree structure. Right. So the first thing that this code does is that it defines some data structures that represent a UI. The primary thing that we have, so this VDOM node is the tree structure in Rust. I heard that Rust makes trees and lists and things like that very difficult, but I didn't face any difficulty for this. The only difficulties that I faced with linked lists and stuff in Rust is that whenever I had to have back references, right? Otherwise, this seemed to work fine. And I don't know if that's the case, like if I'm doing something special, but it just seemed to work for me. It's okay. So here's what VDOM node looks like. It has two separate, yes, sorry, I'm not looking at the chat, but sometimes the messages pop up. I did use a vec for the list, and I'm going to show you where. So there are a couple of things here, right? So first, a VDOM node can either be a plain text, right? And there are a bunch of different type parameters that are passed to a VDOM node. So in this case, the text needs nothing. It doesn't have any children. So the children type parameter doesn't make sense. It just has a state, and it doesn't have any attributes, right? So text is the simplest type of node that you can have in the tree. The other type of node, and there could be more types of nodes here as well, but for now, I've just done these two. The other type of node is a wrapper node, which has children, right? So here, an LM, I call it an LM, it basically has some children, it has a state, and the node itself has some attributes, right? And an attribute here is just a map from string to something else, right? And that something else could either be a string, or it could be an event listener. So I can say on click, execute this event listener, right? So these are the two types of nodes. And then I've basically separated out the internal structures. So LM is a wrapper over this, which has name, attributes, children, and state. And then a text, again, I've abstracted that out into its own structure. It's text and string. That's all it does. So state here is, for my specific purposes, it's either nothing. So it would be just a unit data type like this, right? Which has no information. Or it would be the node that is actually present in the UI, right? So we can hold references to actual user interface elements. So when you create a virtual DOM text node, you can also, when you put it inside the actual UI, you basically created an element very imperatively, and we hold references to that. So the state is basically to hold that reference, but potentially it could hold other state as well. But this is the major thing that we need to hold right now. Right? Okay. So this is what happens, right? So first step is building the UI, and that is basically encapsulated in this separate function. It's a separate function because earlier I had put it in an implementation block for VDom, and I was doing a very mutatey thing, and it turned out to be a lot more trouble than it was worth. Rust makes having a Rust makes interfacing between two sorts of things very difficult. So if there is, if you want to do things in a functional way where you take in ownership of the inputs and then you change them and then you return not references but the actual ownership as well. So that is one world, and the other world is where you take in a mutable reference to that object and then you mutate it and then you don't have to return anything back. So if you write code in both those ways, like some functions take ownership and some functions don't take ownership, it becomes a lot harder for things to mesh well together and for code to be clean. That's my experience. So I eventually ended up writing the entire thing as separate functions, right? Separate pure functions that take ownership of their inputs. Except for some places where it didn't make sense, so I'll point those out. But basically, so build is one function. It takes a VDom, which is a virtual DOM with no state, which means it has not been populated into the UI yet. And it returns a VDom with state, which means it has been populated into the UI right now, right? So that's what build does. It takes a conceptual representation of the UI and populates it into the actual UI window. And the way it does is that because this is a recursive tree, it knows how to build text. It knows how to build the top level of LM. So it builds those by creating elements. And then it recursively invokes itself on the children. So if you've been passed an LM, it will create a node for the wrapper element. And then it will just go inside and do the same for all the children elements, right? So there's a bit of recursion going on here. So here's the recursion, right? So for all the children that were passed, and you can see that the type of children is a VDOM without a node parameter. So it's not been populated. So I basically map over them, and then I append. So I build each of them individually. This is the recursive call. And I append them to the parent node, the wrapper node that was created, right? And then finally, I return ownership of the rebuilt UI DOM that holds references to elements in the DOM. Right, so building is the first step. That's task one for the VDom library. The second task that a VDom library has to do is that it has to be able to stop a UI, right? So sometimes elements need to be removed from the UI. So that function is called halt, and it basically takes a VDom which has been populated into the library. And you can see how Rust or any statically typed language will make it safer, that here we are taking something that has been populated because the state is of type node. And we know that then every node in this VDom tree will have a reference to an actual UI element, right? So we know that this is populated into the UI because of type safety. And then it will basically just remove it from the DOM. And this is very simple. It just, again, recursively goes through the entire tree, gets the DOM nodes out of every single node, and then just removes them. If a parent was found, if it was actually populated inside some object, it will just go ahead and remove it. And the reason why it looks for parents is because it needs, sometimes you can have detached nodes, which are actually not populated inside the UI, but they're still there, right? So you can detach nodes without destroying them completely. So it has to check for the parent that's actually in the UI somewhere, and then it removes them, right? And then it does this recursively, so it halts all the children nodes as well, right? So it goes through the children and halts them all. So everything is very recursive. And this also happens to take care of event handlers and things like that, right? So if there are any event handlers, it can stop those as well. They can be, this is just a halt and build is just a helper function, so we can ignore that. And then we come to the meat of the entire responsibility of the VDom library, which is given an old VDom and a new VDom, it has to compare the two and then create a list of diffs and then apply them to the UI, right? That is the main purpose of a VDom library. And here there are two approaches that you can take. One is a two-step approach where you basically have another structure for that represents the diffs, or you can say like a patch, right? And then it applies that patch wholesale like a stream to the UI. And the other approach that I've taken, which is a single step approach, is that the code to actually create a diff and the code to apply a diff is very enmeshed together in one function. So instead of creating a separate data structure that represents a diff, I just, at that point, as soon as I know what needs to be done, I just do it in the UI, right? I don't create a separate structure. So usually this kind of a thing is faster, but less flexible, right? Because you're mixing code together. And I just did it for simplicity here. It seems to work fine, right? So here's how it works, right? It basically gets the input DOM, which is, so you will see that there are two parameters. One is a populated DOM. So this is the old DOM, which has been populated, and every node inside it has a reference to a UI element that is visible on the screen. And then it takes the new DOM, which has not been populated yet, and then it diffs it, applies it, and returns the new DOM again, right? So this is the type signature should be clear. And you can ignore the host stuff right now. I will explain that when we come to it. But a host is an abstraction over the UI rendering surface. So a host tells you how to actually create a DOM node, right? Things like that. So, okay. So what it does is it basically goes through all the input, like it recursively goes through the input VDOM. And then for each element, it checks if the existing DOM, the V, also has the same type. So if the input says that, okay, now we need to put a text in, it checks if the input, if the existing VDOM was also text. And if it was text, then it checks if the text contents have changed. If they have changed, then it just sets the text content on the node, right? If they've not changed, then it doesn't do anything because it's effectively a no-op. And then it returns the new state. And again, you can see that this returns owned references. It takes in owned references and it returns owned references because it was just much simpler writing code in a functional way, right? There's no mutation going on here. And then it checks if, if we were given a text, but the existing thing was not a text, it was like a wrapper element. Then at that point, we need to halt the wrapper element, right? Because let's say if it was like a div containing several different elements, right? But we said, okay, now we have to replace it with a single text string. So first we need to destroy all the elements. So it basically calls halt and build, which basically does halt and then builds again. So it halts all the existing wrapper elements, and then it builds the new text element, right? So this is a general scheme. And then the same thing happens with the VDOM LM. So if we were given an LM, then we check if it already was an LM, right? If it was not an LM, let's go down to that case first. If it was not an LM, if it was a text, then again, we do a halt and build. We halt the text node and we rebuild the DOM node, right? So that part is simple. If it was an LM, then we need to do some kind of a diffing, right? So what it does is the very first thing that it checks is if the existing node name is the same as the new node name. So if it's not, if the node name itself has changed, that means a different kind of node. Let's say earlier it was a node that represented a vertical list of elements. And then now it's a node that represents like a single element of some other kind, right? So earlier it was displaying, let's say, comments in a post, and now you've replaced it by a wrapper node that displays the user's photograph, right? For example. So in that case, the names won't match. And then we just need to, if the names don't match, then we end up doing halt and build again. We just, even though they're the same type, we destroy the old ones and we build the new structure again. So the name matching is a fundamental criteria of whether it's the same node. So let's say the name matches. Then the first thing we need to do is update the node attributes. So if and this updating node attributes is a helper function that we can look at later on. But give me 1 second. Give me 1 second. I'm just going to be back. Yeah, sorry about that. So what this does is that it updates the node attributes, and by updating node attributes, it means that it checks the node key, the attribute key. So let's say we had a click handler. So if the keys match, then it basically removes the existing effect handler and puts in a new effect handler, and so on. It updates the node attributes using some algorithm, and then it recursively does the same comparison for children. And because children is an array, so it goes through an array kind of a thing. Here it's calls update children. What this function does is it iterates through the array of the old nodes and the new nodes, and whenever they don't match, it does this VDom step recursively on that set of children, right? So it updates the children, it updates the attributes, and then it returns a new structure, right? Conceptually, it's very simple, but there are technicalities on, because of the borrow checker and making sure that everything is correct and so on. But conceptually, I hope it's clear on how this is happening. And then we have these two functions which update the node attributes and update the children of the node. That's it. That's all a VDom engine is. Any questions on this file? Then I'm just going to show an example, and then I think we'll be done. So if there's any questions on this, I'll be happy to take them.
How does the event listener, like, is this a JavaScript event listener that comes up, or?
That is the host stuff. So I'll show you the host file as well. Let me show you. The host file is this. Okay, so where is the? Okay, it's a lot worse in Rust than Haskell because you can't see all the type signatures clearly. But a host file is basically a way to. Yeah, it's so I called it node instead of host here. But basically, it basically provides a structure that has all these functions, right? It doesn't have to be a JavaScript implementation. This is an abstraction over what all you can do with the UI. So it has functions like set text content of some element, append a child to the element, insert a child before some other element, remove a child, get the parent node of an element. Now, these are all abstracted over this node, which is like a conceptual data structure that represents a reference into the UI, right? So it's all abstracted away. And when you want to actually implement it for, let's say, a JavaScript backend, right? You want to use WebAssembly and then compile it to an actual web page. Then there will be an implementation for this, which I should have. Let me show you that. Oh, actually, hang on. I have it right here, right? Because yeah. So this is actually, it implements it for JavaScript using WebSys. So WebSys is a crate that provides access to the DOM, the web DOM from WebAssembly. So I'm just using that. So when we say node, we basically mean an HTML element now here, right? But the point of this having this host structure separate is to allow it to target any backend. Anything that has a concept of a UI tree where you have wrapper elements, you have text elements, you have children of those wrapper elements, you can do this. Does that answer your question?
Yeah, I see how it connects. Can you also explain the output type of the build function?
Sure. The build function. This thing. Okay. So I think what you're asking is why is it not just a VDOM of node, right?
Correct.
I don't know why. So you will see that VDOM of node is basically just a wrapper over VDOM node vec dom state blah blah blah. I could have just made it a VDOM of Node, but I decided to unwrap it for some reason. I'm not sure why, but it would have made it clearer that I'm returning a VDOM. I think because I'm calling it in a bunch of places where I need to unwrap it anyways, right? So, for example, here, I need to put it inside a VDOM. No, I didn't need to put it inside a VDOM here. Yeah, for example, here. So I needed to get the node out, right? And if I had returned a wrapped element, then I mean, I don't have a good answer for that, but they are isomorphic. So it doesn't matter what you return, right? Essentially, that's what I think of it.
Cool.
So here it's just returning the internal property. That's it.
Cool. Thanks.
Okay. All right. So let's get to any other questions about VDOM or the implementation?
Hey, yeah. So I have a question. Wait, am I?
Sorry, your voice is kind of muffled.
Now.
Yes, now I can hear you.
So actually, I was reading how React does reconciliation under the hood a while back.
Yeah.
So maybe the details not in the perfect. But like I think the biggest challenge which they faced was like when they need to parallelize a lot of this update stuff, right? Like currently, this is more like stop the world G. So
yes. So what React does? Sorry, finish your question, then I'll start.
Continue, then I can, of course, ask.
Okay. So so I haven't looked into React's internals, but like I said, VDOM has some very large stages, right? So when you want to update, right, you have potentially large UI trees. And then you have to compare them. And then you have to implement, you have to basically apply all the changes to an actual UI tree, right? So these are pretty large stages. And when we're talking about, and all this happens when you click on something, for example, right? Or when some kind of an event handler fires. So if you do all of that diffing and patching inside an event handler, while the event handler is running, the browser, anticipating that the DOM is going to change, it will just freeze, right? So the guideline is that the event handler should be very quick, and they should, if possible, they should schedule their updates rather than making the updates inside them, right? So what React does with the new fiber architecture is that it goes one step further. It schedules the updates, and it also breaks up the updates into multiple parts, right? So it basically does slicing, where it will make some change, and then it will allow the browser to do more work, and then it will come back and do some more changes, and then it will again cede control to the browser to do more stuff. So the UI never actually freezes. And you always see a smooth UI, and the entire thing is broken up into maybe potentially hundreds of different updates, right? So that's what React does specifically to break this up. So this library is pretty small, right? It's 200 lines. So it doesn't do that, but yeah, it's something that could be done. You just basically have to take care of a lot of bookkeeping. So you have to make sure that you know where you were when you were updating the DOM. You've reached till this point, and then you have to let go of control. And then at some point later, you will be called again. And you need to pick up where you left off. So it requires bookkeeping, which could be implemented in this one as well.
Okay, that actually answers my question already. So it's more like how CPU schedules are. So
yeah, exactly. With JavaScript, you only have a single thread, so you have to kind of act like the CPU and break it up manually.
Yeah, that's true. That's okay. Yeah. Thanks for all the info.
True. All right. So, any more questions? Nope. Okay. All right. I'm just going to take you through, because I think we're running out of time as well. So I'm just going to take you through a simple example of how to use this. And the way this thing works is you basically create a VDOM. So okay, so this is what's happening here, right? So I have two examples. Oh, actually, I think I right now have, yeah, I have two. So let's first look at the counter example, right? And they both start from here. So what happens is that first you create a VDOM, and I call it a machine because you can see that there are three steps. One is building it, then you step through it, and that's basically the operation of the machine, and then you shut it down, right? So it's and a machine is also it's like a very well-known word that represents state machines, right? So so this is like a state machine. And what it does is it builds a simple text thing which says initializing. So when you start the UI, it will just have a text node on it, which will say initializing while everything else is happening, right? So it populates that, and then it does everything else. Then what it does is, now here is where complications with the Rust ownership system come in. We basically have this machine, this VDOM, right? And if you remember the API, what happens with VDOM is that we basically pass in ownership of the VDOM to the step function, and we get a new VDOM in response, right? So we basically need, and it would be the same even if we needed mutable references, because again, with a mutable reference, you can only have one of them, right? So it's not a problem with the way I wrote the code, but it's a general problem with Rust ownership, right? So now I basically need a global access to this, because what will happen is that we first populate the UI and we created this VDOM. And then there are multiple buttons and UI elements on the screen. When you click on any of them, it needs access to this global VDOM machine to be able to call step on it, right? So, and it needs to access the same machine. It cannot be a new copy of the machine. And the reason why I can't make a copy is because it has references to UI elements, and it has event listeners and things like that, which we don't want to copy, right? So it's not a simple data structure. So it needs a global reference to this, right? And this caused me a lot of trouble trying to figure out how do you do a global reference. And eventually I came up with this, which is that it creates a mutable. So this is one way of doing it. Here I'm creating a mutable reference to host by leaking the reference that I put inside the heap. So when I say box new, here I'm doing it to host, right? But I was doing it to the machine also earlier. So I'm just going to take the host example. So I create a box new with the host, and this basically effectively puts it on the heap. And then I just forget that we put it on the heap, right? So it stays on the heap while the program is running. Because it's on the heap, I can actually mutate it and it will stay in that place. So I get a mutable static reference to this object. And this is apparently not the right way of doing it, because this is effectively a global variable. And since then I've learned that a better way to do it is to have an immutable reference that's inside the heap, but then use interior mutability to do things, which in my opinion is the same as doing this, but apparently that's more accepted in Rust. So I'm probably going to change it to use interior mutability here. So it will just be a normal reference, not a mutable reference. So you basically need global access to host and the VDOM machine. And then, so here I do a global access to the host, but then I use Arc and Mutex for the machine so that I can clone the machine cheaply. So I just need to clone the reference, and I'm using that approach for the machines. So once I have that, once I have the machine set up, I basically create a new VDOM, which in this case I'm calling many counter, right? Which creates 1,000 counting buttons on the page. And then I basically let it run, right? So this will basically just step through the thing, right? And I just need to step through the thing once, because stepping itself will populate the UI, and the rest of the stuff will happen when a button on the UI is clicked. So everything else happens inside the event handlers, right? Which is the normal way UIs work, right? And let's look at now. So this is here I'm using many counter, but let's look at a single counter first, right? How does a single counter work? So a single counter is basically a VDom element. Now this is a tree, a data structure that represents what a counter is. So it's a VDom element that basically has a wrapper element, which I named div, which is a web-centric thing. And then it has no attributes, but in the children, it is another VDom node, which is a button, right? Which I call button. And then the attributes have basically an event handler, which when you click on it, then the event handler, this listener, gets called, right? And then the children basically have just a text node, which represents the count, how many times that the button has been clicked, right? So that's all there is. And the count and the listener are provided to it as attributes. So you can see that this function itself, this is the UI definition. This itself is pure, right? We're not doing any mutation inside it. We're just using the passed in listener and the passed in count. We're not even changing the count at any point of time, right? Now let's look at many counter that basically uses this counter. So many counter has a parameter called n, which represents how many of these counters do we need to create, right? So now this actually does mutation. So it needs to take a host and our VDom machine as parameters. And then what it does is that, so let's say we pass in 1,000. So 1,000 times it creates new listeners, right? Because each button has to have a listener attached to it. So we create a new listener for each of them. And inside the event listener for that particular button, we try to extract the machine reference out of that arc that we had created earlier. And then it just steps through it, right? With the new stuff. So if there are 1,000 counters on the page, you click on any of them, they will mutate that machine, right? So at that point, all the other buttons are invalidated, right? They should not do anything else, right? So at that point, and the way we have structured our code right now, the VDom machine, it does invalidate everything. As soon as you step through the global machine, everything else will be rebuilt, including the listeners, including everything. So it's very inefficient right now, right? This is more of a conceptual thing of how to use it. Later on, so the next step here is to have each button be its own independent entity where it does not touch the rest of the tree, right? So as soon as you press a button, it only affects that button, if we can limit it to that. If that button is supposed to do something else on the page, then obviously it has to reflect there. But if it only touches itself, then I would like to only change the tree at that state, right? And not have to do anything else. The reason why it's not completely inefficient, that is still usable, is that VDom actually does comparisons, which is effectively a form of memoization where it checks if it's the same structure, then don't actually change the UI. So it doesn't actually touch the UI. It only touches this particular button, but it does have to iterate through all the children at least, right? So that's the inefficiency. So yeah, so it just creates those listeners, and then it pushes all the counters that it creates with those listeners into the counters data structure. And that counters is a list of VDOMs. And then it puts all the counters inside a wrapper VDOM called div, right? And then again, so this gives you a VDOM element that can be stepped through. So this is how you write UIs using just VDom libraries. Like I said, a library on top of this will make sure that the updates are much more incremental. And then there would be things like concurrency. You can run multiple VDom trees together on the page, things like that. So those still have to be built in on top of this VDom library. Yeah, I think that's pretty much all from my side. Any more questions? Anything else that I can clarify?
I think Akshay had a question or a request as in to run this demo.
Oh, I can do that. Actually, the thing about that is that, let me do that. That I will have to share. So I will stop sharing my, somehow it's not allowing me to share the entire screen. I think you can only see the Emacs window, right?
Right.
Yeah, so I'll just stop sharing the Emacs window and share a browser just to show you what happens, right? Let me know if you're able to see it.
Yeah, we can see it.
You can see the browser, right? So
yeah.
So this is the application. The way I ran it is, okay, before I go, can you still see the Emacs or not?
Only the Webpack app localhost 8088 window.
Okay. So I'm not going to show you the web side of it. But basically, if you run npm serve in the project, it sets up a local server. And that's all through some crates. I think WebSys itself provides all this. And it sets up this application, right? So this is the application. You click on any of these, it updates all the counters, right? So this is a basic counting thing. All of them share the same state because they update the shared state between all the counters. And there are about 1,000 of these buttons here, right? As you can see, it's fairly snappy. In fact, it's a good opportunity to show you what the performance looks like. So let's refresh this and start recording performance. And then I'm going to click it a bunch of times and stop. And so you can see that, the JS heap does not increase. So there's no memory leak here, right? And it's fairly snappy. I mean, let's look at an event handler. This is too small for me to actually. Not sure where I can. Maybe here. Okay, I will find it later. But basically, the event handlers are fairly snappy in themselves. So it shows that it's fairly quick. So I'm taking like 40 milliseconds per event handler to update like 1,000 buttons. So even without any optimizations, writing it in the simplest way possible, it's still fairly snappy and it doesn't have any leaks or anything. Thanks to the ownership system. Anything else that you would like to see? The next thing that I would like to do is maybe just with this VDom library, implement a benchmark of some kind, just to see how it performs, right, with no optimizations. So there are a bunch of web benchmarks. I want to see how this VDom library does with those, because they all look similar to this. Okay, yeah, I was just saying that I think React does pretty well for an old library, so and obviously it's JavaScript, right? So that comes with its own challenges. WebAssembly is in most cases going to be faster, right? And okay, so Leptos is a library that was recently shared on the FPIndia Telegram group, right? So that looks pretty interesting. That's similar to Solid.js in JavaScript, and that uses fine-grained reactivity. It does not use a virtual DOM. And I've been trying to think of how those concepts can be, and it's very stateful. So that's the drawback. And I've been thinking about how to incorporate that into a more functional setting, make everything immutable and easy to understand. So yeah, I'm looking into. I've been interested in Solid.js, but this is a good chance to look into it because Leptos is Rust, right? So I'm interested in Rust a lot more than I'm interested in JavaScript. All right. Thanks, everyone. That's all from me.